The purpose of this tutorial is to introduce some basic computational fluid dynamics, or CFD, concepts, and show you how to undertake a simple external CFD analysis. During this tutorial, I'll briefly introduce CFD and some basic principles such as the finite volume grid, iterative convergence, and boundary conditions. I'll set up and run a simple external CFD analysis, briefly introducing concepts such as the CFD grid and monitor points, and show how the calculation results converge towards a solution. Finally, I'll show and briefly discuss the results of a simple external analysis. CFD is the term used to describe a family of numerical methods used to calculate the temperature, velocity, and other fluid properties throughout a region of space. CFD applied to buildings provides the designer with information on probable air velocities, pressures and temperatures occurring in and around buildings with specified boundary conditions, including climate, internal heat gains and HVAC systems. Designbuilder CFD is a fully integrated module. This means it can be used on existing Designbuilder models created for simulation or energy code compliance purposes without having to export model data to other software packages. Designbuilder uses the finite volume method, which involves solving a set of partial differential equations describing the transport of momentum, energy, and turbulence quantities. The partial differential equations are converted into a set of simultaneous algebraic equations, and the building space under analysis is divided into a set of adjoining rectilinear cells called the finite volume grid. Algebraic equations are then set up for each grid cell, and the whole set of equations is solved using a numerical method. The numerical calculation principles behind CFD are summarized in the help file. There are a number of excellent learning resources which can be downloaded via the Learn Designbuilder shortcut here on the homepage of the Designbuilder website. The webinar CFD material may be particularly useful in the context of this tutorial. The calculations are not covered in any depth in these tutorials, which focus on the core concepts and processes to enable you to start undertaking CFD analysis in Designbuilder. The calculations are performed iteratively and should normally converge towards a solution if the default CFD settings in Grid have been used. Convergence is achieved when there is an insignificant change in the dependent variables between iterations. This will be discussed in more detail as I work through the external and internal analysis examples. Another important initial concept for CFD analyses is that of boundary conditions. These can be specified in a number of ways and are essentially fixed constraints on the calculation input by the user. For example, surface temperatures and supply air temperatures and flow rates are specified as starting conditions for internal CFD calculations. In Designbuilder, the specification of boundary conditions for external analyses is relatively straightforward and just requires setting the building exposure, wind velocity and wind direction, and this is done using a single dialog box. However, internal analysis boundary conditions are generally more involved and require the addition of boundaries such as zone surface temperatures, airflow rates through exterior windows and vents, supply air diffusers, extract grills, temperature and heat flux patches, and often also the incorporation of model assemblies representing occupants, radiators, fan coil units, heat generating equipment such as computers and servers, etc. These will be discussed in more detail later. Designbuilder CFD can be used for both external and internal building analyses. External analyses are conducted only at site level and provide the distribution of air velocity and pressure around building structures due to wind effect. Internal analyses will be discussed in a later tutorial. which builds on the information provided in this tutorial. The external analysis information can be used to assess pedestrian comfort, to determine local pressures for positioning HVAC intakes and exhausts, to optimise the location of roof lights and openings in natural ventilation designs, to calculate more accurate wind pressure coefficients for calculated natural ventilation simulations, or to look at air turbulence effects on top of or adjacent to a building at the initial stage of a wind turbine feasibility study. To undertake external CFD analysis, we must be at site level. So I select that before clicking on the CFD tab, which produces the new external analysis dialog. External analyses are simpler than internal ones, as you don't need to define any internal boundary conditions. Also, they're isothermal and take account principally of only velocity and pressure. Each Designbuilder project can have one or more CFD analyses, and each CFD analysis can be a different set of results for a different variation on the model. I'll call this analysis tutorial. The default grid used by Designbuilder CFD is a non-uniform rectilinear Cartesian grid, which means that the grid lines are parallel with the major axes and the grid lines are aligned with the major features in the model. Although you can specify a uniform grid if required. We do have the ability to edit the grid once created, and more detail on the CFD grid is included in the internal analysis tutorial. A potential problem when generating the grid is the creation of cells with a high aspect ratio, i.e. long, thin cells, that can lead to instability in the equation solver. In order to avoid such cells, grid lines that are very close together can be merged. The grid line merge tolerance is the maximum dimension that will be used regardless of the major model dimensions. The grid has a significant impact on simulation time and the ability of a model to achieve a fully converged solution, so Designbuilder automatically determines the grid settings. Less experienced users are therefore advised not to adjust the default grid settings unless necessary. The wind velocity is the free stream velocity in meters per second for that location at 10 meters above ground level. The free stream velocity value shown is corrected by Designbuilder depending on the site location, as the wind speed would generally be less in a sheltered urban location than in an exposed rural location. The direction is the wind direction to be used for that particular analysis measured in degrees from the north. So for example, 270 degrees sets the wind direction from the west. I could change any of these values by typing the new value into the relevant box. So here I'll set the wind direction to 270 degrees. Wind data can be found in the weather file shown at site level in the simulation screen, and also from local or national meteorological offices and other sources such as CFD Guide A in the UK. The length, width and height site domain factors are multipliers that are applied to the overall dimensions of the building model in order to arrive at an external volume or domain in which the CFD analysis is carried out. The default factors of 3 are applied to the length and width, and a variable height factor is applied by Designbuilder depending on the model height. The default is 2 for buildings 0 to 10 meters high, 1.8 for buildings greater than 10 meters to 20 meters high, and 1.4 in all other cases. After completing and clicking OK in the new CFD Analysis dialog, you enter the CFD screen. The north arrow is shown here in light grey next to the domain. The red arrow here indicates the wind direction setting, and you can see that the external domain defined by our site domain factors is shown here in dotted lines. Additional functionality is now available in the CFD tab via the toolbar and info panel. There are tools which allow us to edit or reset the grid, show grid statistics, and define monitor points prior to running the analysis. Other options become available once a calculation has been run. When a CFD project is created, a grid is automatically generated for the required model domain by identifying all contained model object vertices and then generating key coordinates from these vertices along the major grid axes. These key coordinates, extended from the X, Y and Z axes across the width, depth and height of the domain respectively, are known as grid lines. Grid lines are grouped together into grid regions, and these regions are initially spaced employing the user-defined grid spacing in order to complete the grid generation. I can press the escape key or use the cancel option from the right mouse button to return to the main CFD screen view. Before running any CFD calculations, we should first check that our grid is suitable for the model geometry. We can do this by clicking on the Show CFD Grid Statistics tool or using the Info panel link. And this indicates that the grid settings are OK. When running an external CFD analysis, you should check that a monitor point has been created externally to the building, as Designbuilder creates one point in the centre of the domain by default. Here we can see that the central default monitor point has been defined above the roof, so that's fine. More detail on grid settings and monitor points will be included in later tutorials. We can now set up the CFD calculation by opening the Calculation Options dialog. The General panel on the left enables you to change some of the calculation settings. However, most of these would normally be left at their default setting unless there is a good reason to change them. Some settings you may wish to consider reviewing are the cell monitor and the dependent variables you wish to see on the residual monitor view. I'll add the X, Y and Z velocity residuals to enable me to view the progress of each variable during the simulation. After setting up the simulation, I press Start. The indicator panel at the bottom left of the screen shows that the CFD simulation is running, and you'll see the residual and cell monitor graphs start to plot in the main screen. You can pause the calculation at any stage to change the cell monitor or residual values, or to view the results in the results screen. You can then restart the calculation as required. The residuals are indicators of the degree of error still remaining in the solution. The solution is considered to have fully converged when the residuals are all less than the termination residual, which is typically set to 10 to the minus 5. The normalized residuals graph here shows whether the solution is converging, in which case the residuals are falling towards the termination residual. Sometimes the residuals will increase, which may indicate a diverging solution. However, it's always worth allowing the simulation to continue for a while, as very often the residuals will increase before dropping again towards the termination value. You can see a temporary divergence of the x, y and z variables here after around 300 iterations. Mass is the key residual, and if that one is converging, the others are also likely to be falling. In this case, the residuals all progress very quickly towards the termination value. There are a number of factors, such as the complexity of the model, the boundary conditions and grid settings, which can have an impact on convergence and the time it takes to reach the termination residual value. These will be discussed in later tutorials. The cell monitor here shows that the x velocity variables stabilizes very quickly, which is another good indicator that the results are achieving convergence. Once the calculation is finished, the indicator at the bottom left of the screen shows that the solution has converged. Clicking the Close button will take you back to the main CFD results screen, where you can review the results by selecting slices in the domain. When I select the Add Slice function, it produces a green movable box within the domain. I can change the orientation of the slice using the grid axis selector at the top of the screen. Left-clicking on one of the other directions enables me to view the information in that direction. For example, here I'll select the y-axis. We can choose the slice through the domain we wish to view simply by moving the box using the mouse and then selecting it with a left click. This displays the data currently requested in display options for that slice. I can cancel the slice either by pressing the escape button on the keyboard or via the right mouse button. The current slice settings show velocity vectors and filled pressure contours, and the key at the bottom of the screen shows how the colours in the slice relate to values of velocity and pressure. I can zoom into my area of interest in the normal way. To look more closely at the results. Here you can see the high pressure region on the upwind west side of the building and the lower pressure regions on the leeward east side and also downstream of the separation point on the roof. Note that a finer grid will show more detailed results but will generally take longer to simulate. Here's the same model with a 0.5 meter CFD grid, which gives greater definition, particularly in areas with more complex airflow patterns. For example, here you can see flow separation occurring at the leading edge of the roof. This was not clearly visible with the larger grid size. I can remove slices either by clicking on the Remove All Slices link in the info panel or using the Add Remove Slice tool. Moving the slice selector onto the existing slice, note that it turns red, and left clicking in the red border to remove it. I'll now select the Z axis and take a horizontal slice approximately halfway up the building. I can then use the normal view tools to orbit the building, or to change to say plan view to get a more appropriate view of the display. The finer grid clearly shows the unstable flow patterns and negative pressure areas, some of which result in flow separation. This tutorial has provided an introduction into some of the fundamental principles underpinning Designbuilder CFD, and I've shown you how to undertake a simple external CFD analysis. The next tutorial in the series will introduce you to internal CFD analysis.